So we're really honored to have tonight Harrison Schmitt, who was either the last person or second to last person to walk on the moon. Which was it? Last step. Okay. So, you know, if you go back to the moon and you find something wrong, you gotta go to him. Who left this mess here? Okay. But he is he's an Apollo astronaut. He was the only scientist among the Apollo astronauts, and therefore the only scientist to do planetary exploration on the sea. And then, of course, he ran for and won U.S. Senate from New Mexico, so he became a senator and did many things there, including supporting the space program. And he's also been active since that time. I know he's been a professor and has developed concepts on making use of lunar resources for fusion energy. Perhaps he'll talk a little bit about that. So what we're going to do, we're going to alter the schedule a little bit. The schedule has him speaking for half an hour, Carol for half an hour, and then the debate. We're going to have him speak for 45 minutes, and then Carol for half an hour, and then the debate. To give him a little more time, because we want to hear from him. So, Harrison Schmitt.
Thanks, Robert. Appreciate it. Great to be with you. I don't think there's anybody in this room that isn't convinced that at some point we should be on Mars. Certainly, I'm not. And in fact, that was one of the purposes of writing the book I wrote in 2006. Gosh, that's almost 10 years ago. Of trying to get not only get the technology developed, but pay for such a exploration program using the helium-3 fusion resources of the moon. But tonight, what I would like to do is wake you up and then see if the path Earth, Moon, Mars makes any sense from an operational point of view, primarily. And by operations, I'm including the whole 9 yards of geopolitics, domestic politics, as well as technology and implementation. Now, just for a quick review, what I see as the major implementation requirements to get to Mars is some catalyst, some geopolitical reality, some economic requirement to stimulate technology, possibly educational crisis in engineering and science. Who says we don't have that? And are all of the above, which really is the case. I think all three of those catalyze, is that the right word? Catalysts, okay, exist today. It's just you've got to recognize them, and the media and the politicians and the public has to recognize them. We also have to have deep space work experience again. It's been several generations since we had that experience. And I mean deep space as being different than nearer space. Nearer space is a reasonably accessible part of our environment now. And if you've got a big enough and reliable enough rocket, you can take part in that experience. Deep space is different. It's much more, there's much more risk involved. It's much less forgiving. And that kind of experience is sadly in short supply today. And it's going to take a continuous set of generations of young implementers. And you'll see throughout my discussion tonight the emphasis on young. And just remember, Apollo was a young person's program. And the only other young person program that began about the same time and is still in place today is the nuclear Navy. We can talk more about that later, but that's a very, very important experience for us to try to take advantage of. How did they stay young? Permanent commitment to deep space exploration and development, and that should be, I think, on a par with commitment to national security. In fact, it's closely related, if not intimately related to national security. Now, some of you are aware that I've suggested that we need a new agency to implement this long-term indefinite program of deep space exploration and potentially settlement. I am not saying that NASA doesn't have its place, and there are many things that it can be doing, but you need to focus an Apollo-style management system on these kinds of problems, and we'll more about that in a moment. That system has to stay young, it has to stay lean, and it has to stay risk taker. Now, very quickly, if we had such an agency and it had a mission, then I would see it have its sole focus as exploration of deep space. It could integrate the three major human spacecraft centers as well as the communication capabilities of the Goddard Center into it. Exploration technology development would be a primary function, as would be human spaceflight planning and operations. Have to be robotic precursors. Lunar and planetary exploration science would clearly be intimately associated with this effort, and space resource delineation would be important. And there I think we have a real opportunity for public access infrastructure and private implementation. I would prefer that the private sector had taken the initiative I suggested 10 years ago, but I don't see that happening. And it certainly is not without precedent to have a public access infrastructure developed on the taxpayer's dime. Something as important as this, it makes a lot of sense. The most important part of a new agency is how you charter it. And learning from the Apollo experience, both positive and negative, we of course need to recruit the best engineering project managers available, continuously recruit them. That agency needs to have full hire and fire authority, which NASA no longer has. Maintain an average workforce of less than 30 years old, maybe even less. As some of you are aware, during Apollo 13, Gene Kranz did a back-of-the-envelope study of the average age of people in mission control, and it was 26 years. And they'd already been working for several years. So you can see that indeed that kind of activity, as well as out in the industrial world, is a young person's activity. They have the stamina, the courage, the commitment, the motivation, patriotism in order to make these things happen. And they don't know how to fail yet. That's very important. You need to institutionalize a responsive, minimally layered, and I call it an Apollo-style management environment. Remember that between November of 1968 and November of 1969, there was a Saturn V launch every 2 months. So you know it can be done. It's just that you've got to commit to an organization that can do it. One thing that NASA lost in the space shuttle era was its internal independent design capability. That was a very important part of the whole program, and it was in addition to that of the contractors, which was important as well. It meant that managers like Von Braun and George Low and others could always have an independent assessment of a problem or an opportunity, and they were not dependent just on one point of view. And for Apollo, we had 100% management reserve, that thanks to Jim Webb, doubling what the engineers thought it would cost to put a man on the moon and return him safely to Earth. But I think that based on what we know now, the experience that we have had, that a 30% management reserve would be adequate at least until the critical design reviews were complete. That management reserve allows you to deal with the unknown unknowns without slipping schedule. If you don't have a management reserve, you slip schedule. And eventually, sometimes you lose the program because of schedule slips. But a management reserve allows you to... we went off the air, didn't we? Try that again. I'm sorry, folks. I don't know what that was all about. Projector's on. Here, I just... think the computer went off. Put it back in.
Here we go. All right.
Well, you're seeing it, I'm not. And finally, again, I mentioned the lesson of the nuclear navy. That's very important. That's been going on for decade after decade. The average age stays about the same. Of course, it's a military program, and they have certain latitude in that respect that NASA has never had, but we need to give it to this new agency. Okay, let's try again. The major implementation hurdles for Mars: unequivocal, sustained, permanent national commitment. There just isn't any choice. It has to be there. Annual funding level, I'm just guessing here. It needs to be studied much more deeply than I have. But something like $15 billion per year, indefinitely, including the management reserve based on some objectives. Unless I just jotted these down for the purposes of tonight, I think we could do it faster than this. We may not be able to do it at all. Okay, let's return to the moon by 2025. We should be able to do that. Lunar settlement by 2030. Public-private capital funding. I see no reason why, at least for the energy resources of the moon, we can't do that, although I've been unsuccessful in the last 10 years. Lunar resource production by 2035, and that's very important for the Mars activity. Mars by 2045, I'd like to do it much sooner than that, but let's be, this illustrates what a sustained commitment is going to take anyway, however you put these numbers together. And Mars settlement, let's talk about that by 2055. That means that some people now alive can be the first Martians. How about that? The technical hurdles, can you read that? Huh? You okay with the yellow? There used to be a picture back there. The transit hurdles, radiation. It was a picture of the space station, by the way. Radiation is going to be an extremely critical thing to take care of, to solve. Zero gravity countermeasures. We've done a lot with the space station work already in countering some of the adverse effects of space adaptation, but we're going to have to be absolutely sure we've got that right. Consumables will be necessary. Maintenance, you've got to remember maintenance. And as a matter of fact, I think that we ought to have as a design concept indefinite life rather than mission life. It changes your perspective, engineering perspective, when you talk about indefinite life of hardware rather than a mission life. Doesn't mean you don't maintain it. It doesn't mean that you don't replace things, but the whole philosophy is it's going to last forever, or at least a number of decades. The crew flight, landing, and return proficiency has to be maintained. We really haven't thought about that, I don't think. How do you do that for multi-month missions in deep space? One way in which you may do it, and we may mention it again later, is that your systems and spacecraft have great redundancy and also serve as simulators. So you basically fly the spacecraft that you are flying, and to maintain that proficiency. And I've always thought that for the Mars mission, you want two landers. To go all that way and pay that cost, you ought to have a backup. And if you can use both of them, then you take enough crewmen for two landings. I think that makes an awful lot of sense. Again, tremendous effort, tremendous cost, and a great deal of risk. You might as well land twice, or at least once. Crew compatibility and useful occupation during the trip. I think they're going to be busy enough with simulation and other things, maintenance and the like, that useful occupation may not be as critical as some think, but nevertheless, it's important to consider. Again, I would recommend 2 landing crews on the first mission. And remember, keep in the back of your mind, there's been a precursor mission. It not only tested out your landing systems, robotic precursor or automated precursor, but you have to take your habitat, you have to get your habitat, your living, your consumables and other things there before the crew arrives, in my opinion. And by the way, you'll see me talk about this again, but one of those landing crews would act as a mission assistance in orbit, not continuous, but mission assistance in orbit. Because of the communication delay, you're not going to be able to do what we did in Apollo. The Earth is not going to be much help, except in data processing and in planning, pre-planning of various activities. Now, the major technical hurdles, pre-settlement now, keep that in mind, are entry, descent, and landing, what we call EDL. Rob Manning and I chaired a session many years ago, workshop on that subject, and learned a lot. And one of the things I learned is landing 40 metric tons, which everybody says the first lander is going to need, is something we don't know how to do. We've done 4 metric tons, we don't know how to do 40. There's going to have to be operational testing high in Earth orbit. That's one of the things your rocket systems will have to be able to help you with. I mentioned the autonomous orbiting mission assistance. Atmosphere and dust. They give you EDL problems, but almost no help, unlike the Earth's atmosphere. Developing high energy propulsion systems that can break you into the Martian atmosphere almost certainly is going to have to be happening, along with the using whatever you can of that atmosphere to help break the descent. And we also, I think, have to begin to very seriously think about and engineer ways in which you can abort to land. You go all that distance, all that cost, and you abort to come back home? I don't think so. You've got to think it through, abort to land, work your problems after you get back on the surface, or get onto the surface. And that unmanned precursor that I mentioned before, obviously can have a beacon on it to which you can land, so you land close enough, you have a surface rendezvous, and that will, I think, make the whole operation, once you're there, much easier. That's a long-term habitat and operations center. The consumables would be there: food, water, oxygen, fuel production, test gear. You're certainly early on going to have to test whether you can get all of those consumables available to you from Mars resources rather than having to bring them every time you come. You'll need the rovers, exploration and analysis equipment, and spare parts, systems, and suits. I hope you all remember that the Apollo suits were qualified for 6 EVAs. After 3 EVAs, I can tell you from experience, they probably could do 6, but they were showing an awful lot of wear and tear. And it was only about 8 or 10 years ago, I realized we did have a single point failure in that suit. It had to do with one cable in the arm, that if it broke, your arm was going to be up like that. And you're pressurized, so how you get back in the lunar module or spacecraft with that? So we did have, but those can all be taken care of with good engineering. We're going to have to definitely have better suits, but still that's an engineering challenge. I'm not getting anything out of this one. These are the exploration challenges that we're going to face. We got 3H gravity on Mars' surface. There is radiation. It won't be as bad as the moon. Most of the radiation you have to deal with is from the zenith, but still that is something you have to be concerned about. Consumables are important, again, challenge to have enough and to produce your own on Mars as soon as you can. And you're going to have, I believe, a nuclear power system of some sort on the surface of Mars. And one of the best places to learn how to have such a system and operate it and what the challenges are going to be will be, of course, the surface of the moon. We'll talk about that here in a moment. Maintenance is going to be critical. A communication delay is something that we'll have to deal with, and we've talked about that already to some degree. Integration of Earth capabilities into exploration planning and analysis, I should add. That great Earth will become that great computer in the sky that allows you to gather analytical information, synthesize the information that's being collected, and make it available for future exploration on that particular mission. Integration of orbital assistance into the activities I think will be an important part of, particularly if you take two landing crews. Forward and back contamination protocols. That may be, to some degree, the Achilles heel of any Mars program. We're going to have to be very careful that we don't scare ourselves to death and because of that, never go to Mars. I am seriously concerned about that. Sample and data analysis, both for sample selection and return, and also in situ hydrosphere, cryosphere core analysis. If we're going to find extant life forms on Mars, I think it'll be at that interface. That's been the geologically stable interface on Mars throughout most of its history. If we had the initiation of complex molecular and replicating life forms on Mars early on that we had on Earth, then if they've survived at that interface. I don't think it'll be very complex, but if they're there, we're going to have to figure out how in the world do you find out that they're there and also keep them there, because you don't know the consequences of exposure. Data synthesis, archiving, and retrieval for real-time utility. That's probably where the Earth comes in and plays a very critical role, is being able to provide that kind of synthesis, archiving, and retrieval, for planning purposes anyway. Now, this slide was to discuss the deep space, or the role of the moon in a Mars program. The moon requires similar deep space operational discipline. It's geopolitically important in its own right. The private government partnership is feasible. An important new science while preparing to go to Mars can be obtained. And in the question of Mars transit, then the moon provides you with a radiation lunar protection through a lunar water jacket. Well, you can produce, by the way, water anywhere on the moon. You don't have to go to the poles for ice. All you do is heat the regolith, and hydrogen reacts with the oxygen-bearing silicates, and you get water. Now you have to heat it to 600-700 degrees C, but with solar energy that shouldn't be a big difficulty. So just remember, you don't have to go to the poles. You may want to for other reasons, but you don't have to go there in order to produce water. Food, I have a very strong feeling the moon is going to be very hospitable to food production, oxygen and nitrogen, propellants, and the like. Shorten the transit time. One of the things that helium-3 fusion is particularly adept at is fusion rockets. And in the vacuum of space, you don't have to worry about a whole bunch of things that you have to worry about here on Earth for power production. And if you can accelerate and decelerate continuously, then you can shorten that transit time and remove some of the risks of transit. We've talked about using the spacecraft as simulators for training, crew compatibility. We may want to evaluate that with extended working stays on the ISS, then on the moon, and then back to the ISS. Basically put together a Mars mission for the crew up to some degree before they actually go to Mars. The role of the moon in test, training, and operational preparation. Embed deep space operational discipline. Lander, habitat, and rover designs can be tested out. There's no reason why you can't use Mars designs on the moon. Dust mitigation is going to be critical on Mars as well as on the moon. nuclear power system design and operation, the same. Small-scale consumable production and experience in doing so, and again, with all four of those, the primary fuels you can produce on the moon, of course, are hydrogen and methane, in addition to the helium-3 for fusion rockets. The role of the moon in tests and training and operational preparation, simulation and tests of real situations on the moon. Nothing beats having real situations. We put together the geology training program for Apollo, the later missions, 13 and beyond, as real-time simulations, but on real problems. And it made all the difference in the world in the attitude as well as the learning of the pilot astronauts. We're going to have to learn how to do autonomous, accelerated entry, descent, and landing. That can be done in various ways at the moon. Beacon landing can be done. Abort to land certainly can be conceptually as well as realistically used. Autonomous exploration, you just you put in the communication delays that are going to be excellent with Mars. The sample and data analysis, the same, and that business of in situ core analysis, avoiding cross-contamination, that certainly can be tested on the moon. Forward and back contamination protocols can be tested. You know, you have submicron dust on the moon, and if you can't keep submicron dust out of your systems and habitats, well then you're not going to do very well on Mars. So the moon is a great place to figure out how to do that. Orbital mission assistance is going to work as well. Now finally, the role of the moon in Mars physiology. Big question is, does 1/6 gravity trigger readaptation sufficient to operate in 3/8 gravity? My guess it does, but I don't know that. We never tested it. We were there 3 days. I felt like I was readapting, but I don't know that. I can't prove it. If the answer is yes, the feedback into design and operational planning will be very important. That means less complexity and less cost. If the answer is no, however, the feedback into design and operational planning will mean more complexity. We may have to develop the 3/8 gravity physiological countermeasures and readaptation protocols, and that readaptation will take time. Once you're on the surface, if you're not adapted, then it'll take time to adapt. A long space station stay before a crew goes to the moon may be something that we want to think. Now this picture that you're not seeing is a picture of the Earth, crescent Earth rising behind the moon, and with the caption, "So before Mars crew has a parting view of the Earth." And this was a Martian sunrise. And for months later, greeted by a Martian sunrise, then it's about time we take another walk on the moon. Thank you very much. Do I have time for questions?
Yes.
Good evening. Thank you for an interesting talk. I have the experience of bringing your moon rocks around to Civil Air Patrol audiences time and again, and I'd like you to refresh me on something. What is that mineral that you got named for yourself, the orange soil?
I don't think anybody has named a mineral for me.
It's in the NASA briefing that you got orange soil, that stuff you found
Yeah,
the
the
last
orange
day.
soil. Well, the orange soil is certainly something that I found. It's made up of little tiny beads of volcanic ash.
Yeah.
Glass.
Glasses and things like that.
The average grain size is 40 microns, so we weren't able to see what it was when we found it. And it is volcanic ash, and it's underlain in that particular location. The geological story is more complex than this, but it's underlain by black beads,
Right.
which are partially devitrified. And because the devitrification changed the iron-titanium ratio, the color changed.
Okay.
And it became very, the glass is actually clear, but the devitrification minerals make it look black.
Yeah, well, that all got rolled up into a story that's a new mineral and it's got your name on it.
Well, that's all right.
Who would argue, right?
You
Okay.
just
Well,
got to
thank
be
you for your
careful how
help.
you say it, but
Indeed.
Okay, I was wondering if we're going to be doing all this training on the moon before going to Mars, does that mean that we'll have to set up habitat and do all of those things as well for an extended stay? Or how does that fit into the plan? Will it be short trips to the moon to do some of these training sessions, learn these protocols? Thank you.
well, I think a lot of that schedule I put together, there's a lot of overlap. And your preparations for Mars probably will go on simultaneously with developing not only the going back to the moon, but actually developing settlements there. I see no reason why we can't have settlements on the moon. And once you can do that, of course, a lot of things come into play, such as tourism and things like that. Because the costs, as long as you're active and continuously active and you have long-term production contracts, the cost of all of this starts to go down. That's a very important component of I think, any future long-term program. And one reason why you want to make that commitment to long-term production contracts. But I would see, yes, the moon is a place for permanent human settlements. The resource support for those settlements will be both potentially fusion power here on Earth and the marketing of space resources, such as we talked about, for other activities, not just Mars, but Earth orbit activities will need those resources as well. Unfortunately, I don't have the microphone yet.
Yes, Dr. Schmidt. Finally, I have a geologist to ask this question. Do you think that there are some interesting interactions going on between the solar wind and our electrical discharges at the Martian surface that are producing things like the blueberries that have gone from one explanation to another?
Specifically the blueberries, no. It doesn't mean there aren't interactions taking place as they take place with the Earth. Aurora, for example, are a part of that interaction. The blueberries, it really didn't surprise me at all, because if you walk around for example, the sandstone cliffs around Chaco Canyon, as I have many times out in New Mexico, you see blueberries. I mean, they're concretions. They're little concretions that have grown in the sandstones. And it's not an unusual geological phenomenon. So the one thing it does require, though, I think, is that Mars' surface had percolating water, very clearly, a lot of percolating water at various times.
What about interesting anionic, cationic discharges at the surface due to the lack of an atmosphere? The solar wind or Aurora's electrical ionosphere goes right to the surface.
Well, it goes close, but there is enough atmosphere to modify that, I think. But you're getting me into an area that I do not claim to have any expertise in at all.
Okay. Well,
all right.
Thanks for that.
Last question? Oh, that's too bad. You'll have another chance, I think.
Good evening, Dave Moran, McLennan Community College. How you doing? So, given that you have the experience to go to space as well as serve our country as a politician, and you have the insight as to the way our political system works, we know that the funding for a lot of this is going to have to come through Congress, and we need 100% commitment from our elected leaders. What do you see as a way to motivate them to, let's make this happen?
Get active in the current political campaign. Somebody, if this is going to happen anytime soon, somebody in the current crop of candidates has got to pick up the ball, and in fact they all should, and say this is important to our national security as well as important to the future of Americans. That I think is critical. So I urge you all to get involved with the various your candidates of choice, and make sure they understand this is an absolutely critical future arena for activity by the United States.
Thank you.
Thank you.